the bell work is set out, it says if a sub n is the term that I want, or is actually the term I'm looking at, then what do I mean by a sub n minus 2? In plain English, what am I talking about? Yeah. That's just two terms before. It's two terms less. If a sub n is my third term, my n is 3, then 3 minus 2 would be 1, which is two terms before. So sometimes it's just easy to look at this stuff and go, okay, if a sub n is the term, subtracting 2 from it would be two terms less, so that would just be two terms before. Maybe, if it lets me right. Well, if n minus 2 would be two terms before, what would n plus 3 be then? What would n plus 3 be? Yeah. It'd be 3 terms after. So if I had a whole list of things and I was looking at a specific term, I would just go 1, 2, 3 terms, and that's the one I'm looking at. So then n plus 100 must just mean 100 terms after. I should probably write after on this one. So that's going to lead me to one question that will probably pop up from the homework. And that was particularly number 13. Number 13 looked like an impossible problem. If you look at number 13, in fact, let's go ahead and write it down. It says, number 13 says, d sub 1 equals 3. So that's my first term. And then it also says that d sub k plus 1 equals 2 times d sub k minus 1. Notice it's not d sub k minus 1, it's d sub k, back up to full script, minus 1. Well, it looks really weird because it says list the next 5 terms. Well, we already know the first term is d sub 1 equals 3. So my next term is d sub 2. But it almost looks like I have to look in the future. It looks like I have to go one step further and see what that one is to get back here. But that is not what it's saying. What this is saying is this d sub k plus 1, that is the term I want. That is the term I want. Whatever's on the left-hand side is basically what I'm looking at. So that's what I want. So that's the term I want to find. Well, right now, I want to find d sub 2. So if this is the term I want, then d sub k is 1 less than the term I want. Because k plus 1 is definitely 1 bigger than k. So what this is actually saying is the term I want equals 2 times the quantity, the term before. Because it is 1 less. And how it looks more mathematical sense-wise, rather than just saying, so the term I want equals 2 times the term before minus 1. What would that look like mathematically is, I'm looking at d sub 2. Well, the only way for d sub k plus 1 to equal d sub 2 is if k equals 1. So in fact, what I actually am looking at is d sub 1 plus 1, where my k equals 1. Well, in that case, we would have d sub 1 plus 1 would equal 2 times d sub 1 minus 1. Well, that's exactly what I said. In plain English, I said, well, it's 2 times the term right before it, which would be 3, minus 1. So this first step would just be 2 times 3 minus 1, which would equal 4. Well, following the same strategy, d sub 3 would just be 2 times the term before it, which is 4, minus 1, which would equal 6. Just like d sub 4 would be the 2 times the term before it, minus 1. So there's two ways to kind of look at this. You can plug in the numbers and make sure it's correct. But a good thing to be able to do is just recognize what it means in plain English. The term I want equals 2 times the quantity of the term right before it minus 1. Because once you have that pattern down, the rest are pretty easy to do, and you don't have to worry about k's and j's and n's and whatever other variable we have in there. It really is just finding that pattern. All right, so that was number 13. What other questions do we have? Yes, Leo.
The one before that.
The one before that. So the one before that was a sub 1 equals 28. And then it says a sub n, the term I want equals a sub n minus 1 plus 3. Well, if the term I want is here, n minus 1 is the term right before it. If this was n minus 2, it would be 2 terms right before it, but this is just minus 1, so it's the term right before it. So all it's asking you to do is take the term right before it and add 3 to it. So that's what we did. We did 28 plus 3. If you're doing this notational-wise, though, we would say a sub, maybe I should do this in red so it stands out a little bit more. So what's actually happening here is I'm looking at a sub 2 equals a sub 2 minus 1 plus 3, which would be a sub 1 plus 3. It is just the term before it. So one method is just in English, and the other method is to actually just fill in your n's. If I'm looking at a sub 2, I'm going to put a 2 in for both of my n's. Do you need more of that one, or is that make sense? Okay, awesome. All right, Grace. 9. I feel like we almost had 2 9s, didn't we? Because I had to go back from a different one. All right, number 9. Number 9 has 1/3, 2 9ths, 4 27ths, and 8 81st, and so on, and so on, and so on. So the top and bottom turn out to actually be powers. The bottom ones are powers of 3, and the top ones are powers of 2. So 3 to the first gives me that 3. 3 squared gives me that 9. 3 to the third equals 27. 3 to the fourth equals 81. Well, if I'm looking at my very first term should be 3 to the first, right? So if I just have 3 to the first, I'd be good there. And for my second term, I could a sub 2 equals something over 3 squared, which would give me 9. So these numbers actually match up. So these are just my n's. So a sub n equals 3 to the n down here. The problem comes with our numerator, because I have to go 2 to the 0th, 2 to the first, 2 squared, 2 to the third. So my first term is actually 2 to the 0th. All right, when I plug a 2 in, I need 2 to the first. So that means when I plug a 2 in, I need it to come out as 1. When I plug a 1 in, I need to get to 0. So that means every time I'm plugging something in, I have to go 1 less. Easiest way to go 1 less is just go, okay, n minus 1. If I plug a 2 in here, it'd be 2 minus 1, which gives me 1, which would be 2 to the first. And that 2 will work down here. So a lot of it's just kind of trial and error. It is looking at those patterns and just trying something. Other questions? All right. 10. All right, 10 is kind of the same thing as that one. We are looking at powers of 2 in our denominator. We have 2 to the first, 2 squared, 2 third, 2 to the fourth. So that's just 2 to the n, because my first term should be 2 to the first. When I plug 1 in, I should get a 1 here. So that's just 2 to the n. The only problem with this one is it also alternates between positive and negative. So that means I need to use this -1 to some power. And I picked -1 to the n minus 1. Since the first term is positive, if I plug a 1 in for this n, I have 1 minus 1, which is 0. -1 to the 0th is positive, so that one will fit my situation. The other one I might have tried is I might have also tried negative 1 to the nth power. But if I plug a 1 in here, I come up with a negative, which would mean my first term is negative, so that one would not work. So you just have to know one of those two would work, that positive and negative. Yeah?
I got a question on 11, so it's fine, but can you do number 10?
Oh, did you say number 10?
Yeah.
Oh, okay, sorry.
No, you're good.
Number 10 is, well, we'll talk a lot more about 10 today, but it is, we're just adding 2. It doesn't look like it, but we really are just adding 2. Because this negative 1 to the n minus 1 will tackle this positive and negative. So I forget about the positive and negative, and I go, well, the numbers actually are 2, 4, 6, 8, 10. Well, that means we are adding 2, adding 2, adding 2. And we'll talk more about this later, but basically you just take your first term. We'll talk more about this today. You'll see how to do this one today a lot better. Other questions? Hope?
Number 6 on
Yeah. All right. So those factorial ones. So those factorial ones, we have on top, we have 2n minus 1 factorial. On the bottom, we have 2n plus 1 factorial. Now let's go back to what it means to be a factorial. If I ask you to do 8 factorial, I think most of us understand that it's 8 times 7 times 6 times 5 times 4 and so on and so forth. But what I think people forget is that 8 factorial only works that way because it is 8 times 8 minus 1 times 8 minus 2 times 8 minus 3. It is always one level down. But that's how every factorial works. Every factorial works by subtracting 1 to get to your next step. So if I look at my numerator, my numerator isn't actually going to help me, but if I look at it, I can rewrite 2n minus 1 factorial is going to equal 2n minus 1 times 2n. To get to my next step, I just subtract 1 from it. So I have 2n minus 1 minus another 1, which would be minus 2. Then one step down would be 2n minus 3. But that one doesn't really help me that much. What one is going to really help me is the denominator, the 2n plus 1 factorial. So using that same idea, our factorial starts with what we're given, 2n plus 1. Then we go down one step. We have to subtract 1 from it to get to our next step. So that is 2n plus 1 minus 1, which is in fact just 2n. And then my next step would be 2n minus 1. But that's exactly where I want to stop. Because we could continue on, but we can also put a factorial right after it. We could just stop there and say, well, the whole pattern continues after that. And why that's important is because we can rewrite our original equation as 2n minus 1 factorial all over 2n plus 1 times 2n times 2n minus 1 factorial. And our 2n minus 1 factorials will actually cancel out. And we'll be just left with 1 over, and we can distribute that to be 4n squared plus 2n. So you have to recognize which factorial is bigger and keep subtracting 1 until it looks like the top or the bottom in that case. So for number 7, if we look at number 7 really quick. Uh-oh. If we look at 7, we're going to see I looked at the top and said that's bigger. 3n plus 1 is bigger than 3n. So I looked at it and I said, well, 3n plus 1, factorial is 3n plus 1 times 1 less, which is 3n. And I could have stopped there and just put a factorial symbol there and we could have crossed it out. I just showed that they would be the exact same thing as the top and the bottom. But you can definitely end right when you get that match, and you can just write this as 3n factorial over that factorial here. So you really have to go back to, you're just subtracting 1 to get to the next level. And you actually have to do that math. No longer can you just go, it's 9, 8, 7, 6, 5, 4, 3, 2, 1. You have to go, okay, it's 13n plus 60, and then it's 13n plus 59 plus 58. Does that answer your question? All right, other questions? Okay, I'm not going to wait because we do have a lot to get through. As I was telling Mary, we're going to cover what her question was right now. We're going to actually take a step back. Yesterday was kind of throwing you in the deep end, and today we'll take a step back and just focus on one type of sequence, and that is an arithmetic sequence. An arithmetic sequence is a sequence whose consecutive terms have a common difference. So they have a common difference. In other words, sequences a sub 1, a sub 2, a sub 3, so on and so forth, is an arithmetic if there is a number d such that a sub n or a sub 2 minus a sub 1 equals a sub 3 minus a sub 2 equals a sub 4 minus a sub 3, which all equals d. More commonly, maybe a better way to put it, it is your 2, 4, 6, 8, 10, where you just keep adding 2 over and over and over. Or you subtract 4 over and over and over. What that common difference is can you add or subtract a number over and over and over and get to every element of your sequence? And that's exactly what an arithmetic sequence is adding or subtracting over and over and over again. So, some examples. Are the following arithmetic sequences? If so, state the common difference. So our first one, this is exactly what we're going to do every single time you check a sequence. You're going to see if there's a number you can add over and over and over or subtract. So you're going to go, how do I get from 1 to 5? Well, that is adding 4. To get from 5 to 9, I add 4. To get from 9 to 13, I'm going to add 4. That means, yes, it is arithmetic. And it's got a common difference, which we're going to use a lowercase d equals 4. So a lowercase d is going to stand for our common difference. Sometimes you have to be careful. So if we look at the next one, I have 1, 7 over 6. I have 4 over 3, 3 over 2. It doesn't look like I'm adding or subtracting anything. But they also don't have a common denominator that I could even see if they're being added or subtracted. So oftentimes when I have fractions, I'm going to look for, is there a common denominator that's going to help me get all of them? So a common denominator in this case would just be 6. So I'd rewrite 1 as 6 over 6. I'd rewrite 7 over 6 as just 7 over 6. Can't really change that. 4 over 3 would become 8 over 6. And finally, 3 over 2 would become 9 over 6, and so on and so forth. Well, now there is a pattern. We are adding 1 over 6 to each of these. 1 over 6 is being added to each of these. So yes, it's arithmetic because we are adding 1 over 6. So yes, it's arithmetic, and our common difference is going to be a positive 1 over 6. Our last one is not going to be arithmetic, because if I look at it, we are going to add 3. Then we're going to add 5. As soon as I added 5, you don't have to check any further, but we can go further. This is plus 7. There is no common difference. I'm not adding the same number over and over and over. I'm adding 3, 5, and 7. So this is just no. It is not arithmetic. So if I ask you to do anything with an arithmetic, you just can't with that one. All right, so arithmetic is your basic sequence. It is the one you're looking for every single time. Well, as soon as I realize that it's an arithmetic sequence, you can immediately write a recursive and explicit formula based upon finding your common difference and knowing your very first term. So the first thing we're going to cover is our recursive formula. Our recursive formula is just going to be a sub n is always going to equal a sub n minus 1 plus our common difference. That is our recursive. So really, for your recursive, you just need to know your d value, because all of this is going to stay the same anytime I ask for a recursive. Explicit formula, on the other hand, we need to know a little bit more about it, and I did write the first one first. Okay, so we have a sub n is going to equal our very first term, so that is a sub 1, so that is something you need to know, plus your common difference times n minus 1. It's kind of a clunky way to write it, so a lot of times we just distribute the d and we move our a sub 1, and we actually rewrite this as, so this is another way to rewrite it, or you can write it as a sub n equals d times n plus a sub 1 minus d. But really that's just a simplified form, because I really just distributed this d. That's where I came up with my d sub n, or d times n. I distribute this d here and I get my negative d. That's where that came from. This is a much simpler way to work with it a lot of times. So you look at my answer key, I'll write both of them. But I typically prefer this one later on because it's just an easier formula to use. All right, so that's our recursive and that's our explicit formulas. As soon as we find our d, we have our recursive. As soon as I have the common difference and I have my first term, I can write an explicit formula right off the bat as long as it's arithmetic. So let's go ahead and do that. So we have determined whether each sequence is arithmetic. If so, write two formulas for a sub n. Two formulas means I need to write a recursive and I need to write an explicit formula. That's all the two mean. All right, so the first thing I have to do is check to make sure it's arithmetic. When you check for arithmetic, you're also checking to figure out what your common difference is. So to get from 3 to 7, I add 4. To get from 7 to 11, we add 4. I add 4. I add 4. So yes, in fact, it is arithmetic, and it has a common difference of 4, and I'm also going to list the very first term. That's what I'm always going to do. As soon as I figure out something's arithmetic, I'll list the first term and my common difference. Common difference is 4. My very first term is 3. Recursive formula is always going to be, for an arithmetic sequence, you're always going to do the exact same thing. You're going to go a sub n is going to equal a sub n minus 1. Now all we have to do is tack on our common difference. So that is just plus 4. We also have to put one more thing in our recursive formula. A recursive formula, you have to know what your first term is going to be. So in a recursive formula, when we actually have numbers, we should say a sub 1 equals 3. So we need to write where it starts. We need to write the starting point. Explicit formula is just going to be a sub n is going to equal our very first term, our a sub 1. So that's 3 plus our d value, which is 4, times n minus 1. Or we can distribute that 4, and we're going to end up with 4n minus 4, so that's going to be minus 1. If I distribute that 4 to the negative 1, I do my a minus my b. Either one of those is the exact same formula. you should at the very least check mentally to make sure these formulas make sense. So that's why I have a little check on this one. So to check it, for my recursive formula, my a sub 1 is 3. My a sub 2 is the term before plus 4. So that'd be 3 plus 4, which equals 7. Yeah, that's what it should be. My third term should be the term before it, plus 4, which equals 11. And if we keep going, it's always going to work. So that checks out just fine. For our explicit formula, I just check one or two of them. My third term should be 15, correct? So if I plug a 3 in for my ends, I should get out 15. So let's check that. So a sub 3 is going to equal 4 times 3 minus 1, which is going to equal 11. Well, my third term is 11. So that one worked out. My fourth term, that's the one that's supposed to be 15, not the third one. That's what got me for a second. My fourth term should be 15, so if I plug in a sub 4 in, we'd have 4 times 4 minus 1, which would equal 15. You just got to check a couple of those, and it's not hard to do mentally. All right? If a couple of them work, most likely all of them are going to work. So that is just your check. That is most of the time you just do it mentally, but it can save you a bunch of points on a test. Yes?
Can your common difference be negative?
It can absolutely be negative. Yep. In fact, they will be negative at times. Yep. And then everything stays the same, except like this would be a negative 4. So this would be minus 4. And this would be a minus 4 as well. Oh, in fact, that's what we do have next. We have 5, 2, negative 1, negative 4. To get from 5 to 2, we do have a negative 3 difference. Then we subtract 3. Then we subtract 3. So this is an example where our common difference equals a negative 3. And I always list my first term off so I remember it. A sub 1 equals 5. Our recursive formula, we should say where we start. So I'm going to say a sub 1 equals 5. And now my recursive formula is always going to be a sub n equals a sub n minus 1 plus 5. In other words, it is always the term I want equals the term before it. It should be a minus 3, not plus 5. It should always be the term I want equals the term before it plus our common difference. In this case, it'd be minus 3. So the term before it, then subtract 3, and you get to your next term. All it's saying is keep subtracting 3 over and over and over. Our explicit is going to be a sub n is going to equal our first term, which is 5, plus our common difference, which is negative 3. So I'm going to have minus 3 times n minus 1. Or we could distribute that and turn it at h sub n equals negative 3 times n would be negative 3n. Negative 3 times a negative 1 would be a positive 3, plus 5 would be a positive 8. Just be aware that both of these are the exact same formula. One is just simplified, one is just the expanded form. You'd also probably check that at the very least in your head. Your recursive, it's really hard to mess up because it is take the one before and subtract 3. So if we start at 5 and I subtract 3, we're going to have 2. Boom. Subtract 3, we're going to have negative 1. So it's hard to mess this up unless you just have no idea what the formula is. This one can be a little harder, so I would check maybe the third term being negative 1. Well, that means I'd plug a 3 in here, 3 in here. We'd have negative 9 plus 8 would equal a negative 1. And you can try it with 4, you can try it with 2, you can try it with 1. It's going to work for all of those. I highly encourage, at the very least, you check in your head. On a test, it's always a good idea just to write it out really quick to make sure you have the right one. All right, judging by the amount of space I gave you for this next one, we probably don't have to do much work. And that is because this would be plus 4. This would be plus 12. That's all I need to say this is not arithmetic. So you don't need to do any more work. Because I said if it's arithmetic, come up with two equations. It's not, so I don't have to do any more work. All right, our last one says the following is an arithmetic sequence. So I'm starting off telling you what it is. You have to write two formulas based upon those 2 bits of information. So they give me my third term is 15 and my 8th term is 50. So that means we kind of have a lot of gaps. So we have a sub 1 equals, I don't know, a sub 2 equals, I don't know. I actually want to move those over just a little bit because I need some room off to this left-hand side. A sub 3, I got that guy. That equals 15. A sub 4, I don't know. A sub 5, I don't know. A sub 6, I don't know. A sub 7, no. That's a Z. That's a 7. A sub 8, that is the only thing I know is that 15 and that 50. But what's going to help us get our 2 equations is knowing its arithmetic sequence. Since it's an arithmetic sequence, there is a number that I would add to get to 4. That same number would get me to 5. That same number would get me to 6. That same number would get me to 7. That same number would get me to 8. So in other words, to get from 3 to 4, I would add D, my common difference. Then I would add a common difference again to get to 5. Then I would add a common difference to get to 6. Then I would add a common difference to get to 7. Then I would add a common difference to get to 8. So to get from 15 to 50, I'm going to add the same number 1, 2, 3, 4, 5 times. Well, going from 3 to 8, that's 5 steps. So I didn't need to write all this out. We just kind of did it so you see where I'm getting my information from. But to get from 5 to 8, that is 5 steps. And that is 5 D's I need to add. So we're going to start with 15. We're going to come up with an equation. We start with 15. And that needs to equal 50. But it can't just equal 50. We need to add 5D to it, and then it will equal 50. So 15 plus D plus D plus D plus D plus D would equal 50, and now we just solve that equation. So we're going to have 5D equals 35. So our common difference is just going to be 7. Cool. 2 things I need is a common difference, and I need my first term, and I come up with my 2 equations. So the only thing I'm missing now is my first term. How would I get my first term in this one? What's one method I could do? Yeah. I could absolutely subtract 14 from 15. So I could just go, okay, if my common difference is 7, I can just subtract 7 and subtract 7, which is awesome here. But what if I give you a sub 30 and then I give you a sub 36? Do you really want to subtract a number a billion times? You can. It'll definitely work. This will get your answer is 1. So a sub 1 equals 1. Here's another way to solve it if you don't want to keep subtracting a number over and over or count all your steps. So another way you can do it. So this is fine. This gets me my a sub 1, just subtracting 7 over and over and over. So do it if you want to do it that way. The other thing we can do is we can say, okay, our formula for any explicit form of an arithmetic sequence is a sub 1 plus d times n minus 1. Well, I know the third term. I know a sub 3. I also know the common difference is 7. I also know if I'm looking at the third term, my n would be 3. Well, a sub 3 actually equaled 15, which is going to equal my first term plus 7 times 2, which would be 14, which would give me a sub 1 equals 1. use any method you want to. Because you can count on how many steps it is, and you can just multiply it. That's really what's happening here, is how many steps there are between the two, and then multiplying it that way. All right, as soon as I have my first term and my common difference, we have a recursive, and we have an explicit formula we can write. Recursive formula, we should list the starting off point, that is a sub 1 equals 1. And then our formula is just always going to be a sub n equals the term before it, which is a sub n minus 1. And then we add our common difference, which is 7. Explicit formula is a sub n equals our first term, which is 1, plus our common difference times n minus 1. Maybe I'll put an equal sign on this one, which is going to be the same thing as 7n. Well, 7 times a negative 1 is negative 7, plus 1 is minus 6. Here is my recursive. Boop, 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 boop. Here is my explicit. Doot, 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 doot. And that covers arithmetic sequences. Mary, do you think that'll help you on that one? That was just adding, yeah. Like I said, yesterday was kind of thrown to the deep end. Now we'll take a step back and just focus on arithmetic sequences. All right, any questions for me? I am not going to check your homework today because several of us had questions. I want to give you a chance to finish it, check your answers, and be able to get your full points for the homework, the previous homework, the one from last night. So if you have it done and it's all corrected, then you're good. If you don't have it done and corrected, make sure that gets done this weekend as long as this assignment as well. This assignment should go a little quicker than last night's because it really is exactly what we just did in the notes. Find your common difference, find your first term. As soon as you have those, you have a recursive and you have an explicit formula. All right, the rest of the time is yours to